Welcome to today's webinar, a cool take on hot EV batteries, navigating thermal propagation with CFD based on thermal runaway kinetics modeling, brought to you by Convergent Science and IAV GmbH. Thank you for joining us today for the 14th installment of the 2024 Converge webinar series. My name is Matthias Sulis and I am part of the business development team at Convergent Science. I will be your host for today's event. I'm glad I can be here with you today and learn directly from our partner at IAV about thermal propagation with CFD and thermal runaway kinetics modeling using Converge. Convergent Science is a rapidly growing computational fluid dynamics software company. Our flagship product, Converge, is an industry-leading CFD solver used around the globe to simulate fluid flows in complex systems. Converge features truly autonomous meshing, which eliminates all user meshing time and helps provide fast, accurate results for our client. IAV is an international company based in Berlin, Germany, that has been developing technical solutions for the automotive industry for over 40 years. They are dedicated to providing the best expertise and methodology to their customer to help them tackle challenging engineering problems, such as thermal propagation in electric vehicle batteries. Now it is time to introduce our speakers for today's event, Kislaya Srivastava and Lorenz von Roemer. Kislaya is currently a principal research engineer at Convergent Science in Northville, Michigan. He earned his Master of Science from the University of Michigan Ann Arbor in mechanical engineering, specializing in thermal and fluid science. He has 7 years of industry experience applying computational fluid dynamics and other numerical tools to simulate and analyze a wide variety of complex fluid flows and heat transfer problems. Lorenz is an R&D engineer at IAV with over 7 years of experience in CFD simulation of internal combustion engines. He specialized in simulating combustion processes with alternative fuels such as hydrogen and methanol, as well as thermal runaway and propagation in EV batteries using Converge. During today's webinar, if you have questions for Kislaya, Lorenz, or the team at Convergent Science, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. Without any further delay, I will now pass the ball to Kislaya and Lorenz. Thank you all.
Okay, so I will start right away also without any stop. So why should we look at thermal propagation or thermal runaway and thermal propagation in the first place, and why should it be mitigated? So as you can see here in this picture, the first thing is that it's for safety, right? So people's lives are in danger when the battery is taking fire, and this fire can really hardly be extinguished from the outside. So especially in case of an accident, for example, it can be very crucial to save lives, to have thermal propagation under control. Of course, we have also the impact on the environment, and also the public perception is very negative if you see in the newspapers that cars of a specific brand, for example, are taking fire more often than other ones. Especially also if for the OEMs, it's also very expensive also to call back vehicles that are seeing this kind of thermal propagation. How is thermal runaway and thermal propagation working? So we have, first of all, the thermal runaway, which is at a cell level when the cell starts to heat up and getting on fire. If this cell then can propagate this heat exothermal reaction to its neighboring cells, so more on a module or on a pack level, then we call that thermal propagation. And here's the point. So what's happening, the thermal runaway is super hard to avoid because you have it because of manufacturing problems or other causes, like, for example, what we have here on the left-hand side, low temperature charging, mechanical deformation, so in case of an accident, etc. But what we want to avoid is then to have the thermal propagation. This causes then lead to like the electrolyte degradation, and then to a short circuit and to this exothermic self-heating, which then leads to the thermal runaway and eventually thermal propagation. So what we have done is we wanted to look on a experimental side how, and also on the CFD side, how is thermal runaway working and thermal propagation, and how can we do a modeling of that. So in the first of all, we started with an experimental campaign, just looking at a cell level, so just one single cell, and we put that cell into this thermal runaway. The thermal runaway can be reached with different technologies, so heating up the cell, having a nail penetration test, and then this cell would eventually go into this thermal runaway. For that, we have at IAV our test bench, which is for this dedicated studies of cell destruction. Then the next step was to look at it on at CFD. So we build up the exact same single cell model we had in the experiment, and we applied the same boundary conditions, and we validated then this model to the experiment to have an accurate model of this thermal runaway also in CFD. The next level was, because we are also super interested in the thermal propagation, is to do similar experiments, but not only with one cell, but in a module with different cells, or with more than one cell. So we put 7 cells together in a module where the central cell was then penetrated with a nail, and that one then saw thermal runaway, and we would see if the neighboring cells would go into the runaway as well. And we were trying different mitigation technologies to see if we have some technologies that work better or less better to avoid the propagation. And same here also, we modeled then this exact case in CFD with the different mitigation technologies with exact same geometry, and we took the calibrations we had from the single cell CFD study, and we tested that also in CFD. And as a step further then on a pack level, module level, then we have been looking even at other geometries with the same chemistry, for example, and then to apply it also to a real application in an electric vehicle. So we have been looking at different cell chemistries. As you can see here in the middle, we've been looking at NMC 811 cells, we've been looking at LFP cells, we've been looking at SAB cells. All the cells we've been looking at were cylindrical cells, and the trigger to get them into the thermal runaway was constant heating, where we just apply a constant heat source on the outside of the cell. You can see that this heating pad over here, and we also have a heat wake seek procedure. So it means that we heat up for a certain while, then we wait a bit, then we heat again, and we continue heating bit by bit over time to see at what specific temperature the cell is running into this thermal runaway. Another pretty common test is also the nail penetration. The nail penetration is to simulate, for example, an accident, so the mechanical deformation of the cell, and which can also lead to this thermal runaway. All the single cell tests were done in a nitrogen environment, and we also changed some of the periphery of the cell. So we had at some point cell holders, which would also affect the thermal pathway of the heat. We had some insulating foils we applied on the cells, and also some different positions of this insulating foil. And as you can see on this image is here, so these are the cells, the different cells, NMC, LFP, and SIB, that went into the thermal runaway. So that's how a cell would look like after this kind of testing. Let's go quickly to one of the results. So this is the NMC case with constant heating. And this is how the cell was built up. So we have here, the cell is this dark purple color, and we have two holders here. We have the heating pad here, which is heating up the cell, and we have the the positive terminal here and the negative terminal here. And we placed different kinds of, as you could see earlier, of thermocouples, which are measuring the temperatures on the cell. And as you can see here, we can directly see how the cell goes into this thermal runaway, and the temperatures are getting higher, especially also some gas temperatures we measured, where you can see that the temperature peak is really, really high. And then we would have here later on a cool down phase after the runaway. In this picture, that was the optical access to our autoclave, where you can see the cell that is positioned here. It is standing and holded by the two clamps over here. And as you can easily see, there are some strong sparks and fire coming out of the cell. So that's the moment where the cell is having this thermal runaway. The next step is now to get this cell into a CFD model and simulate the exact same behavior we see here. And for that, these temperature curves that are placed on the cell are important for the calibration process in CFD. And for that, I would like to hand over to Kislaya, who is going to present the CFD calibration process now.
Thank you, Lorenz. We'll begin our discussion by a quick introduction on how CONVERGE CFD has been applied to a wide variety of detailed 3D battery simulations. CONVERGE CFD software is well suited for battery simulations requiring 3D coupled flows, associated heat transfer, and chemistry in complex geometries. Our autonomous mesh generation capabilities allow you to easily mesh and simulate complex battery pack geometries, and our adaptive mesh refinement guarantees optimal spatial resolution for a given mesh count in order to reduce your total time to solution. We have run simulations of battery thermal management looking at air-cooled, liquid-cooled, immersion-cooled batteries, and also more recently, more novel phase change material cooling. We have simplistic 0D models or more detailed 3D models with electrochemistry in order to incorporate heat release rates within the battery under normal operating conditions. Our focus, however, has mainly been in the complex problem of battery thermal runaway. CONVERGE contains the computationally efficient stage detailed chemical kinetic solver, which has been adopted to model thermal runaway chemistry and associated heat release inside the solid. We rely on established Arrhenius-based chemical reaction mechanisms to model thermal runaway in 3D. Now, different batteries will have different thermal runaway behaviors, so we need to calibrate a thermal runaway reaction mechanism to reproduce experimental data. In order to do that, we have developed a couple of tools. We have developed the ARC fit tool, or the accelerated rate calorimetry data fit tool, and also a DSC, or differential scanning calorimetry data fit tool. This allows you to optimize, calibrate, and also construct multi-step reaction mechanisms catered to your particular battery. Once you have a reliable thermal runaway reaction mechanisms, you can go ahead and do more multi-physics simulations of vent gas ejection, vent gas combustion, solid ejecta, etc. Talking more about the thermal runaway mechanisms in Converge, one of the thermal runaway mechanisms we offer is the Ren thermal runaway mechanism as proposed by the listed author here. This is developed for an NMC battery chemistry. It consists of 6 reactions: the reaction for the SCI film decomposition, reaction between anode electrolyte, cathode anode, the cathode decomposition process, and also some set of binder-related reactions. If you look at the reaction format, it is very similar to the Arrhenius format we come across for fuel oxidation problems. So all of the expertise we have modeling gas-phase combustion chemistry has been easily applied to model thermal runaway chemistry inside the solid. Thermal runaway reaction rates are calculated for each of these individual 6 reactions. They take into account local species composition and also local temperatures. So all of this is done in 3D. We accumulate all the heat release for all these individual reactions and feed it inside your battery solid. With the well-established reaction mechanism, we are able to reproduce experimental results or experimental battery data. Now, as mentioned before, selection of a suitable thermal runaway mechanism is essential in order to reliably achieve predictiveness in your converged 3D CFD models. Different batteries will have different chemistries and they will have different associated thermal runaway behavior as shown here. If you just use different thermal runaway mechanisms or slightly change the mechanism, you will get very different thermal runaway behavior for the same particular problem. So our workflow involves taking those single cell experimental data that Lorenz just showcased and trying to reproduce experimental behavior and trying to match the experimental heat release rate profiles as shown here with a calibrated thermal runaway mechanism. To calibrate a thermal runaway mechanism, we go back to the reaction rate formats and we try to optimize or tune the values of the pre-exponential factor, the activation energy, the reaction order, and the reaction enthalpy. And in order to aid users to calibrate their thermal runaway reaction mechanisms and all the associated parameters, we have developed an optimization algorithm utility that allows you to tune those reaction kinetic parameters and minimize the error between your simulation predictions and your experiments. Here we obtained experimental data for an ARC, heat weight seek type arc data, and then we calibrated a 2-step thermal runaway reaction mechanism. The original mechanism shown in green was over-predicting thermal runaway behavior, but once it was optimized, it was able to accurately reproduce experimental thermal runaway characteristics. Now we'll go ahead and discuss the IAV case setup. We made a selection of the NMC 811 constant heating case, and we used the Ren mechanism to reproduce thermal runaway behavior. The thermocouples 3, 4, and 5 were selected to be reliable for the calibration process. As Lorenz mentioned, 1 and 2 were measuring gas temperatures during the thermal runaway event, and we are not modeling gas for this particular case. And 6 and 7 were ignored due to the close proximity to the heater pad. The Converge model, as shown here, was a solid-only 3D simulation. The different solids were included for, along with their accurate thermal properties, were included for the 18650 NMC cell, the heater pad, and also the clamps. This is a transient process. So the clamps add a thermal mass in your system. It's a conduction pathway for heat loss from the battery to the clamps and to the ambient, and also leads to some 3D effects inside the solid. Since we're not modeling a fluid in this particular simulation, all of the outer walls are modeled with the convection temperature boundary condition to enable heat loss to the surroundings, which was present in the experiments. There was an uncertainty on what the heat loss to the surrounding is going to be, and in order to remove that uncertainty, we ran an initial warm-up simulation, and then we calibrated a heat transfer coefficient on an HTC value for the boundaries shown, the outer boundary shown here. Below 400 Kelvin, we don't expect too much thermal runaway reactions to occur, so we can assume that this profile, calibrated value of HTC, will well match the thermocouple profile. If we continue to run the case, we notice that the results start to deviate even at lower temperatures. We went back to the experimental images and experimental movies, and we found out that at around 340 seconds, we got our first venting event. So due to the first venting event, you will notice in your experiment evaporative cooling inside the battery, which will lead to drop in thermocouple predictions. And we have come across this in the past when we were trying to validate the Wren mechanism. The default Wren mechanism does not incorporate a reaction for electrolyte vaporization, which is an endothermic reaction, which absorbs heat. And this reaction becomes prominent at lower temperatures or lower heating rates. When we augmented the default Wren mechanism and added an extra energy sink term to account for vaporization, as shown here, we were able to accurately match experimental behavior. This is now also important for the IAV experiments. So for the IAV case setup, we incorporated evaporative cooling by adding a calibrated heat sink term starting at the experimentally observed first venting time, around 340 seconds. The calibrated value for this evaporative cooling energy sink matched well with our expectation of typical mass of free electrolyte inside a typical 18650 cell and typical heat of vaporization for a typical electrolyte, as shown in this literature here. Once we have all those uncertainties figured out, we went ahead and calibrated the Wren mechanism. We used the optimization utility, and we were able to get a well-calibrated Wren thermal runaway mechanism that accurately reproduces experimental behavior. Now, during this calibration exercise, we also wanted to ensure that the calibrated mechanism is meaningful and makes physical sense. In reality, the thermal runaway process follows a particular sort of reaction order. Initially, at lower temperatures, you have the self-heating due to SCI decomposition. Then you have the anode electrolyte reactions kicking in that elevate temperatures further and kickstart thermal runaway onset. And at elevated temperatures, you have your binder reactions and later on your cathode decomposition reactions. And we were able to enforce this particular reaction order as seen here, initial SCI consumption, and then later on anode electrolyte, cathode, anode, and then later on the cathode decomposition. So our calibrated mechanism made physical sense and was expected to be reliable for a wide variety of problems. Once we got a calibrated Wren mechanism, we forwarded that mechanism to IAV engineers. They constructed easy converge simulations for a heat weight seek experiment and a nail penetration experiment, and that calibrated mechanism accurately reproduced the experimental behavior for those different tests. So we can be confident that our calibrated mechanism will work well for different types of simulation scenarios. We were also fortunate enough that IAV provided us experimental data for different battery chemistries, so we can check the robustness of our calibration exercise, calibration approach, and robustness of different thermal runaway mechanisms available in literature. We received data for lithium iron phosphate on an LFP battery chemistry. In literature, we found evidence, or we found researchers trying to employ the Hatchard-Kim four-step thermal runaway mechanism. So we calibrated the default Hatchard-Kim thermal runaway mechanism and optimized it to mimic the LFP data we received from IAV, and we match very well with the experimental data. We also received data for a relatively new battery chemistry for sodium-ion batteries. For the sodium-ion batteries, there were some uncertainties on the battery properties. We were not fully confident that we had the correct battery properties, but we were still able to get well-calibrated multi-step thermal runaway mechanisms for SIB data. And just to show the versatility of this calibration approach, we were able to calibrate a four-step, a two-step, and even a one-step thermal runaway mechanism to experimental data. Now, more recently, we have further improved our calibration approach and our simulation approach. Previously, our simulations were dealing with fixed battery mass, fixed battery density. So curve in red, you can see that we weren't capturing the cool down trend after the thermal runaway event correctly. In reality, the battery in the experiment had a 65% mass loss. And most of the mass was lost during the thermal runaway event through solid ejecta. And this will have an effect on the subsequent battery cooldown because you have a different thermal mass. And it's also important to consider when you do module level simulations because a battery with lower thermal mass has lower energy to transfer through conduction to adjacent cells. And this is something you want to include in your simulation framework and also include dynamic battery thermal mass reduction during the thermal runaway process. In order to make the mass reduction more predictive and having experiments to guide us, we coupled the mass loss equation to the late stage reactions for binders and the cathode decomposition process. So as you can see here, there's a dynamic reduction of battery mass during the simulation. And now, as you can see with the curve in orange, we get the correct cool down trend. And now we have a much more optimized thermal runaway mechanism, thermal runaway behavior in our simulations. In the future, we also want to investigate very quickly the effect of different cathode materials. We did tests for NMC 811. We want to look at other NMC cathodes, but we don't want to do expensive tests for the full battery. We also have a DSC data fit tool where you can take experimental data for individual battery materials. Shown here is just the DSC calorimetry data for just the NMC cathode, not the full battery. So you would go to Converge Studio under the DSC data fit tool. You would enter the DSC data for different scanning rates into this tool. You will take your established cathode reaction format, and this tool will calibrate just the cathode reaction mechanism to that experimental data. So what we're able to achieve through sort of a simulation framework is, for the same battery, if you just switch between different cathode materials, get a new cathode reaction, what is its effect on thermal runaway propagation for your module or for your pack? And as you can see, as expected, NMC 811 is more risky for thermal runaway propagation scenarios. And NMC 323 is a more safer design. So we hope to continue working with IAV to sort of investigate different cathode materials, different cathode chemistries, etc., easily with this particular tool. Something we also want to keep in mind is thermal runaway behavior is a chaotic behavior, and we want to treat it as a statistical problem. Researchers at University of Tennessee have showcased that for the same battery, the same chemistry, and repeated tests, you get very different thermal runaway behavior. So this is something to keep in mind. We want to do more experimental tests and give us a full understanding of the statistical nature of the thermal runaway problem. We have run statistical simulations for battery thermal runaway propagation and presented it at the NASA battery workshop. We have taken multiple experimental data for the same battery, converted them to statistical significant thermal runaway reaction parameters, and then explored a wide subset or wide design set for your thermal runaway propagation problem. And now once you have a full understanding of a thermal runaway process and a well-calibrated mechanism, you can move ahead and include more physics into your simulation involving vent gas ejection, vent gas combustion, solid particle ejection, and so forth. With that, I would like to hand the mic back to Lorenz.
Thank you a lot, Kislaya. All right, so yes, thank you very much. So for the following study, so this calibration is also very important and crucial. First of all, I want to go into the thermal propagation testing. So what we did here is, you can see here the module with its 7 cells, where the central cell was penetrated with a nail. You can see it here in red. And then we have been also having a lot of thermocouples placed on all over the cells, as you can see here. So this is the module here, and all these cables coming out are the cables for the thermocouples, to have a track of what is happening inside the module and see if we have the thermal propagation or not. We've been also having a optical access to see what is happening in the autoclave with the module. Yeah, let's go right through the results. So as you can see here, so at the beginning, so that's when we start to the nail penetration into the central cell. We see that sparks are coming out of the module, and so that the central cell is getting into a thermal runaway. As we can see here, 1.5 minutes later, the runaway is taking place, and we have even more sparks and first flames coming out of the autoclave. of the module. What you see in the next one is then the ignition of all the vent gases mixing up with the air. So in this case, we have air as environment gas, which is ignited, and we have the whole autoclave, so all outside the module, starting to burn, and we have this big fire here taking place. And later on, this fire gets lower, and we see here that we have also the neighboring cells going into the thermal runaway. So maybe look here down at this graph. So this is a small comparison between a case we did with air as ambient gas. So that's the one you see in the top line, and in a second case where we have nitrogen as environment gas. And the as you can see here, so the dotted lines are the air case, and the straight lines are the nitrogen case. And we are looking here at the temperature in cell 7. Cell 7 is the central cell, which is seeing the nail. And we can see that the temperature increases strongly when the nail is penetrated, and that's at 0 seconds. In the case with nitrogen, we see that this temperature increase is not as high as we see in the other case. It's because in the module we have already the air which is inside the module starting to burn in the air case, which is not the case in the nitrogen case. In the nitrogen case, we just have the composition, the species composition of what is coming out of the cell, which is burning and getting into this thermal runaway of the central cell. If we look now to the next one, we can see here, so these are thermocouples which are placed in one of the neighboring cells. So in this case is cell number 1. You can see that in the air case we have a high increase in temperature. So again, as in the cell 7, which is a central cell. So we are seeing here a thermal runaway of this cell, so a thermal propagation from the central cell to a neighboring cell, but which is not the case in for the nitrogen case. So we see here that the ambient gas composition has a strong impact on the thermal propagation. If we look here at the validation, so what we did, as mentioned before, we built a model of the module, and having also the nail and the 7 cells and the gas in between the cells, so it's a CHT approach here, and we have also all the different parts of the module which are represented here. And if we look, for example, at this case here, we're having then the comparison between the CFD and the measurement. The measurement are the dashed lines, and the CFD simulation are the straight lines. And we can see that we have here a for the thermal runaway, so the central cell here, we have a good match between measurement and simulation. So this is a result after the calibration that Kislaya just showed us earlier. And also on the neighboring cells, we see as well that with the boundary conditions, so what is happening in the module, that in this case we don't see the thermal propagation taking place. Here in another case where we have a strong thermal propagation, we can see that the green line would be the central cell, and all the blue lines are the outer cells, where we can see that after the first line is seeing the thermal runaway, all the neighboring cells are seeing also a thermal runaway pretty much simultaneously, all of them in this case. And again, here we have a pressure trace from the measurement where we can see that all this thermal runaway and propagation is a good match with what we see in the module in the experiment. We have been looking also at different kind of boundary conditions, so with the goal to see how we can mitigate the thermal propagation. What we have here, for example, is we have a intercell material, which is here symbolically represented by these blue surfaces. So these blue surfaces are this intercell material, and this intercell material should delay the thermal propagation. As we can see here in this plot, these areas here are the results from the measurement, and we can see here the first cell is going into thermal runaway, and then here a bit later some other cells are seeing the thermal runaway. If we take this same intercell material and the properties especially, and we add them into our CFD model and run the simulation again, we get the green and the blue curves, where the green curve again is the central cell and the blue curves are the outer cells. And what we can see here is a similar behavior as in the experiment, where we have the first cell seeing the thermal runaway right with the nail penetration, and the outer cells seeing with a delay the thermal runaway. And we have marked with these orange lines the differences between the measurement and the simulation, and we come to the result that the delta T between the experiment and the simulation was a maximum of 10%. So which is here a fairly good approach to see if thermal propagation is taking place or not. In the left case, we have a total different a material. So we have here a fluid. The cells are immersed in a fluid, and what we see in the experiment, so that's the purple curves, that the central cell is first seeing the runaway, and then the outer cells are seeing this runaway almost simultaneously. And if we try this out also in the CFD, we see here again that we see the same behavior as in the experiment. So also here we have also the validation for other intercell materials, or even other, not only gases but also fluids as material in between the cells. Further on, then we have been looking at some other kind of materials. We have been looking not in the experiment, but then predictive in the CFD. And what we have here is our reference case, which is a reference gap filler. We see we have right now in different EVs. And we have been tested it for the thermal runaway. So we see here, these are the dark blue curves, and the dashed curve is always the central cell, and the straight curve then the neighboring cells. And we can see that right after the central cell is seeing the thermal runaway, we have the propagation to the neighboring cells. As a different material, we have been checking also in a insulating foam, which is then the blue curves, and the insulating foam compared to our reference gap filler has a lower conductivity, a lower density, and has a similar CP value. And we can see that the neighboring cells are getting triggered in a later, so delayed in compared to our reference case. So that the insulating foam here works to at least delay the thermal propagation. The same is visible also here in the heat release curves. Last but not least, also a phase change material, so that's represented in purple, and this one has also to our reference a lower conductivity and lower density, but a higher CP value. And what we can see here is that at least for our duration here, we see no thermal propagation, so the neighboring cells are not seeing the thermal runaway in this case. Phase change materials are in this case very interesting, but they come with another additional challenges like the price, also the packaging must then be changed. So regarding the efficiency of the battery, we have to find a compromise here. Other interesting procedures also to avoid the mitigation would be to have a an immersed cooling. So we have been testing here it for different kind of oils with different temperatures and also with different velocities. So the plots are the same here as in the slide before, and you can see here, for example, the difference between our standard gap filler, which is the same as before, compared to an oil at 50 degrees, which has lower conductivity, lower density, and a slightly higher CP, that the thermal propagation is delayed compared to our base case. But what we see here is that the adjacent cells are going into thermal runaway almost simultaneously. So we don't have this delayed propagation where one neighboring cell is seeing the runaway first, then another cell. If the oil is a bit cooler, we see it that the delay is even stronger. So here we went from 50 degrees centigrade to 30 degrees centigrade, where then we have a delay of this thermal propagation. And then another case, this purple curves over here, if we add even a velocity to this oil, then in our case, we didn't see any propagation. So immersion cooling could be another procedure to avoid thermal propagation. So in summary, we can say that especially safety, stricter legislation, and avoiding image damage require no thermal propagation batteries. And in this study, Convergent Science and IAV, we have been evaluated different thermal runaway and thermal propagation mitigation technologies using the battery chemistry and conjugated heat transfer in our CFD simulations. These simulations can help. So in this predictive simulation approach, we helps to find the optimal configuration for our batteries, because as mentioned before, we're having here a compromise between the battery efficiency and the thermal propagation mitigation. And together with Convergent Science, IAV are still proceeding in working together in for more advanced achievements in this complex field of thermal runaway and thermal propagation. For that, thank you very much for your attention.